In this video tutorial, we're going to show how to model and design a 3-span continuous post-tension beam in Adapt Builder. We'll be using Builder 2019 for this example. Now, before we launch Builder, we want to make sure we set up our specific selections for the modules we'll be using. And to design beams, to evaluate beams, it's similar to a floor slab in Builder. So we're going to be using Floor Pro. We want the ability to model post-tensioning, so for the mode we'll set up PTRC. And we're going to be doing everything inside of Builder, so we don't really need the option to export out to Adapt PTRC, which is our 2D frame program that allows you to design beams and slabs. We'll be using the US unit system here for this example. And we're going to assume here that we have, I'll just kind of sketch up what we're going to be looking at. We're going to have 3 spans, columns above and below, and we're going to fix the base of the columns here. We'll do a column over here. This is going to be, let's say, 10 feet and 10 feet. We'll just use the default heights. Those can actually be set up here in the reference plane manager. The user can also go here to model under story manager, and the same thing can be done there. So this plane that we're really working on, that we're modeling on, this is called current plane. The far end of the top columns is top plane, and far end of the bottom columns is called the bottom plane. Okay, and we're going to add some loads here. We'll add 20 PSF. That's probably a little too much for a parking slab, but we'll say 20 PSF super dead and 40 PSF unreduced live load. So those are the loads we'll be adding to the structure in addition to just the self weight. The spans that we're going to be looking at today, we're actually just going to do 3 spans. The spans are going to be identical in length. Okay, so the spans here we're going to say are going to be, this will be 66 feet, this will be 60 feet, and then we'll do another 60-foot span. The actual member sizes here, we're going to say that this beam here is going to be, let's say, a 24 by 38. This will be 24 by 38, and this will be 24 by 42. Now this beam, beam 1, let's say span 1 and span 2, are referenced from this current plane downward. The slab that we're going to be using is, let's say, 6-inch slab for the flange. This beam in the middle, this might be at a ramp, so we're actually going to move this beam up. It varies, but here we're going to see this ramp is actually up 16 inches. Okay, so the first thing we want to do is actually get the model in place, and we're going to use a few tools to help us do that. We're going to be modeling in the XY plane down here in the global axis. We're in the XY plane, vertical positive upward is the Z direction. And so the first thing I'll do is actually set up just a grid. This is just a snap grid that we're using, not our actual formal set of grid lines, but in the X direction we're just going to we'll just say that grid here is, let's say, 10 by 10. And I'm going to set up a column. The columns we're going to assume are 24 by 24. So if I invoke a column from model, we'll say this is 24 inches by 24 inches, and I'll place that column. Now this next column over will be 66. This is at 10-foot spacing, so I'm actually going to copy that over, and I'll just go here to modify by coordinates, and I'll copy it in the X direction, the positive X, 66 feet. We'll say copy, and then I'll copy this over. So these grids really did not offer us much help. They will offer us a little help with the flange. We'll make it useful for the flange when we go ahead and model that. This column we're going to say we're going to replicate that 2 times at a 60-foot spacing. So we'll copy those over, and now what we'll do is just model the beams. So the beams by default are actually going to be flush with the current plane at the top. And I'll go to the item properties immediately. I'll just change the beam sizing here. We'll say these beams are 24 by 42. That's the first span. Okay, we'll go from column to column, and you'll notice that actually picked up that snap grid. So sometimes it's a little bit difficult if this is near the column. I'll just turn that off for a moment, and then we'll bring that back on here in a moment. So I'll use snap to endpoint. The snap tools are centered down on this bottom user access bar, or you can get them from the home menu. There's a snap tools panel here. So actually my problem there was I just didn't have that snap tool turned on. So let's go back. I'm going to change this beam size, the depth actually, to 38 38 inches. Select the checkbox to accept that change, and now I'll just model 2 additional beams. So we have our beams. If I flip this to its side, you can see this is our frame. I'm actually going to take these columns and just copy them vertically. So if I use modify, copy, vertical, I'm going to copy those up one time, like so. And right now we're actually working in what we call single level mode. This is really important when using the software. This is single level mode. So notice that here this is highlighted red. That means this is the current plane in single level. If I actually switch this to multi-level mode, nothing really happens. Everything looks the same, but what would happen in the background is the boundary conditions on the columns would actually switch, and they would be pertaining to the setting. If we go to criteria, analysis, and design options, they would pertain to the setting here. So for single level, we use one set of boundary conditions. If we run a model in multi-level, we use another set. And so this model, it's really just one series of beams. We're going to stick within this realm of single level mode pretty much for the entire time. The next thing we want to do is actually push this beam up. Okay, so we'll select that beam, and I'm just going to double click on it, go to location, and a negative value is upward. I'll say this is actually offset upward 16 inches. So that allows us to step the beam. If I rotate this to 3D, we can kind of see the system we've built here. The next thing, I want to add the slabs or the flange. So to model this, I want to be back not in the ZX plane, I want to be back in the XY plane. I'll just flip this back here to top view. I'm back in that top view. And if I turn on my grid again, we want to have a 28 or let's say a 300 inch flange. And so we want the grid setting to be basically 300 over 2. So 150 inches, if we convert that to feet, we want the grid to be 12.5 feet. And we're going to just set this to 12.5 here. This will make things hopefully a little bit easier. You'll notice when I do that, this is actually not centered on that grid. So this actually may not be as helpful either. So let's go back and let's just make this flange divisible by 10, because that's kind of where we had started our columns. All right, let me turn this grid back on. All right, so we have 10 feet this way, 10 feet that way. We're going to make this flange, let's say, 240 inches. Okay, so now because this is stepped, I actually need to create 3 unique slab regions. We'll go to Model, Slab, and we're going to just model this. Now notice here, this doesn't really correlate with the position of that column. So I'm going to abandon the use of that grid, and I'm actually going to use construction lines. We don't really have a background to build this, so I want to use some construction lines. I'll go to Home, create a line, and I need a point, basically an intersection to move this point over so it's in projected, from this column up, it's in line with that column. So I'll take this and I'll actually just use snap perpendicular and just move it and position it there, and then I can move this over like so. Okay, now I could just take this, Control C, Control V, or I could draw a new one and I could do the same thing again, but we'll realign this first. So I'll use my line tool again. I'm just going to go perpendicular there and there, and just shift that over. And then one more time here, I'll actually just draw in the slab. Notice, this is just at some arbitrary location, so we could use these lines also. Here I want to have this, in the orthogonal, let's say X direction, parallel with these beams. So I could turn on this option for snap orthogonal, and that allows me to align these construction lines orthogonally. And here I can just grab that and now just move it down. So there's different ways to kind of model the components natively and align things. This is just one particular way of doing that. But ultimately we have now our slabs. Now if we don't want these lines in the model, if we don't want to see those, we can always go to Select by Type, Line, and I'll just remove them. They were just there to align the slabs. If I go back to this view, notice this slab is actually at the reference plane, at the current plane. So I want to push that slab upward, and I'll go ahead and just offset the slab also. So we'll take that slab location wise and we'll raise that up to 16 inches also. And now what we have is this model. So we have a stepped beam in the middle. Visibility wise, if I go to visibility rendering, you can see there's the model right there. Okay, so you can confirm it here. And let me just go ahead and save this model. All right, the next step is we want to add some loads. So I'm going to go ahead and take these slabs, I'm going to select them, and I'm going to map loads directly to them. So we'll go to loading. The load cases that we're using are here under the general loads. Building loads don't really apply to this type of a model, so do not add loads here. These are really for multi-story models, so we're going to just assign all of our loads from the designated load cases here. You could add load cases to this dialog, but we'll say this is superimposed dead and live load. So the dead load we're going to add using the patch load wizard, and for dead load I'll say this is 20 PSF, 0.02 KSF is the entry, and for live load we'll do 0.04. Those are our loads. Now if you need to get into load viewing, I could turn loads off and on here. I could turn on dimensions, control kind of the visibility and what you're seeing here, but this is where you would control the loading. It's under the loading ribbon, the visibility panel. The next step will be to add a support line, a frame line. I want to make design cuts along the path of these beams so that I can obtain actions and actually get a design for the beam. So we'll go ahead to floor design. I'm going to go to create an X support line. This is in the X direction. So we'll go ahead and just go from column to column to column. And notice I'm still working in orthogonal mode. That can be restrictive when we're modeling support lines. So I'll turn that off and just kind of narrow down to use of this endpoint tool for snapping, and that makes it easier to enter that. Now I've pressed enter to close the line. I'll press escape to close out of that command altogether. And if I generate the sections, you can see the user has control over some of the inputs for these design strips. You can set the criteria. In this case, the criteria we want to use is a beam. And under design section options, I can dictate how many design cuts I want, minimum or maximum spacing, minimum number of cuts or maximum number of cuts per span, and so on. If I want the program to consider the effective flange for the beam, we could actually use this option here, effective flange width. So this allows a user to invoke effective properties for the design of the beam. We'll actually use that for this case. The next step will be to add some post-tensioning. Now one difference between this program and Adapt PTRC is that this program requires the user to at least enter the post-tensioning to begin with. And so this beam is going to be, we're going to add some fairly unique, let's say, post-tensioning first. The first thing we're going to do, just for the sake of showing how to model the tendons, and then also maybe a starting point, will be to determine what level of post-tensioning we need, the number of strands we need just to meet pre-compression in the beam. So let's assume our target pre-compression is 150 psi. It's about 0.8, 0.9, 0.85, 0.9 MPa if we're converting it to SI equivalent. So this section, we see we have the area of the section is calculated as 2740. So if we take 2740 and we multiply that by 150, that's our pre-compression times the area, we get 411 kips. And we're going to assume that for a 1/2 inch diameter unbonded cable, we get around 26.7 kips per strand. So if we take 411 divided by 26.7, we get 15 strands. We're going to bump that up to 16. So I'm going to model 16 tendons on this beam, just to start. And so we'll go ahead and do that. Let me turn off the strip. We've already developed the strip. I'm going to now turn that off. You can control the strip visibility here from Floor Design under the strip visibility panel. And I'm going to go here to Tendons, and I'm just going to add a tendon. And I'll add this tendon from anchor point to high point, anchor point. That models the actual tendon spans. If we double click on that tendon, we have some entries here that we can make for the tendon. We said we need 16 strands to start. We'll say 16 strands. These are 1/2 inch diameter. I could also, instead of using single entry for 4s, I could say, well, no, I'm going to just say I want 411 kips. That's what we entered for, or that's the calculation for the pre-compression, and that actually is 15.39 strands. So 2 ways you can do that in this version of the software. In versions prior to 2019 build 2, you had to use entry of multiple strands. In other words, you couldn't use this total force entry. It was not available in older versions. So let's say this is 16 strands. Under shape, we're going to dictate the profile. So this anchor point over here, this is actually half the depth of each beam. Now, if we wanted to know what the CG was for the section, we could double click on the design cut, and I could see the centroid to the top fiber is actually 10.3 inches. I'll just round to 10, and so we'll use that for, let's say, the anchor point. So the user can define where that anchor point is on the end. We'll say instead of 21, we're going to say it's 10 over on this end. Actually, I should have gathered the other number too, because that's a different section. On the opposite end, we're going to go, let's say 9 inches. So I'll turn off that strip again. I'll come back into my tendon properties, and I forgot to save that. Let me press that green checkbox. So this is 10 inches. We're going to say the CG from the bottom here, we'll say that's 2 inches, 2 and 2. These are all reverse parabolas. We could change the shape of the profile if needed. And then over on this side, this is 9. From the top down here, this is actually referencing from this slab or this top of beam here. So we're going to say that that's also 2 inches down. Let's say we want a little more clearance there, maybe 3 inches. And let's do 3 inches here. Okay, so that is in essence the first tendon that we're going to add. Now here in this middle span, we don't really have a lot of drape because we're dictated by the tendon kind of cutting through this edge here and this edge. So we might actually have to add additional tendons that are anchored up higher and drape down in order to control the stress in that span. I'll show you how to model that. We're not going to go through the entire design process of doing that, but we'll show you how you can model that also. So this is our starting point for the post-tensioning. If I go to criteria, under allowable stresses, we can go in beam and then set up some of our design criteria for beam. The program is going to code check against these allowable stress values. They can be modified by the user as needed. Right now we're kind of working in that bottom end or bottom limit of the transition zone if we're designing per ACI. This design code is currently set to ACI 14. For concrete material, we're going to change this to 5,000. You could add as many materials as needed. In this case, everything is currently assigned to concrete 1, so we just changed the material there to 5,000. So the next step, just to begin kind of the design iterations in the process, we're going to mesh the system. So I'll mesh this. I'm going to execute the analysis, and these are default combinations found under loading, load combinations. You can add to these. Here our targets are really just determine, let's say the requirements for serviceability, pre-compression, allowable stresses, balance loading, and then beyond that, if we're looking at deflections, we can look at that in more detail. So strength, we're not going to really worry about until we have some outcome for the post-tensioning cables necessary to control the serviceability conditions for the beam. So we'll just design and analyze now for those combinations. After I'm done analyzing, I'm going to immediately go here to floor design. We've already generated our cuts. If we have not yet, we should generate the sections and then design the sections. Okay, once we've designed the sections, I do not really want to see these mesh shells or elements, let's say. So we're going to turn the cells off. I'll go here to visibility, view settings. Under finite element, I can turn off the shell/cell element. I could also do that under analysis, visibility, and turn on this option here. So this is our beam. We're looking at a top view. We've analyzed, we've designed. I'm going to go over here now into this result browser. Under analysis, design sections, we're evaluating the sections which are being evaluated as beams. They're really T-beam sections. So if I look at actions for the selected combination, I can change that combination in here. Ignore load cases, that's not really important in this case. So we're really looking at load combinations. And we're going to say for this, let's look at the bending actions. So these are the bending moments for this frame. And we can turn those on if we use this numerical display on/off. This one shows all values. This shows, max min values. If I don't want to see all the cut lines, I can turn those off. But this gives us just the moments along the span, moments, shears, axial force, etc. So we could just look at actions. Our real main concern here might be stresses. So if I look at the precompression, we can see in the beam the max precompression. The range is from 154 to 160, so it varies slightly, but we're kind of hitting that target of precompression that we wanted. And this is being code checked by the allowable under display, and we're code checking only against minimum allowable precompression. So we actually have this set to 125. If I change that, let's say, to 150, we're still going to be okay because everything is really over 150. That gray just kind of encroached on the actual values which are shown in green. So precompression is fine for now. Balance loading, if we look at the load balancing on this beam, we have 68, 43, 81. That's per simplified method. We could also look at the FEM method. And we're kind of hitting target-wise. This says it's okay because it's actually less than maximum balance loading of 100%. What is going on here is the bottom stress is no good. So in this first span, this is a 66-foot span, we have bottom stress that exceeds the code. The allowable here of 7.5 square root of F prime C. And let me just change the number of significant digits here to 1. That might help us see the values a little bit better. So the max stress here in flexural stress-wise is about 665. And the allowable, if we look at the allowable, 5,000 square root times 7.5, so it's around 530. So we're over slightly. The other two spans were okay. So depending on what we want to do here, we probably don't want to hit these other spans maybe with post-tensioning because we have an opportunity to really just do an add tendon here and pull that out of this member. We could either do that manually or we can use what's called the Tendon Optimizer. So this is similar to like the recycler in Adapt PTRC. What I'll do is go up here to Tendon, and I'm actually going to turn off this graph for a moment. It's a little bit too busy for me there, and we're going to let me go back to visibility default display, and I'll just turn on the tendon. I'll just show the tendons. And I'm going to go here to Tendon Optimizer. In Tendon Optimizer, I'm going to go to Settings, and we want to make sure we set up our optimization settings. We're going to optimize. We don't really need to optimize on precompression. We're going to optimize on balance loading and stress. For service total, this is actually going to be beam criteria, and we can report the stresses as a ratio, a factor. This is a 7.5, or the actual stress. There's our allowable of 530. And we can set up our precompression balance loading ranges. So we set up our desired targets here. And the next thing we're going to do is actually optimize that tendon. So I'll just select that. And it's asking me to enter the tributary width. We know that the tributary width is 20 feet. program is going to create a virtual span. Essentially, this blue box is really a span, and you can see that the program generates a section cut A, section cut B, and C. And A and C are actually quite a ways away from the face of the column. We actually want to optimize closer to the column face. So what we'll do there is we're going to come over here to settings and say, well, the percentage of span where we want those first cuts, we're going to reduce that down to 2. I haven't actually calculated this, but that's pretty close. A and C are now right near the face. If I go back to Optimizer, you can see the program is actually itemizing kind of the tendons in the beam. There's 16 strands, there's a CG of 2, effective force of 26.7, and it's saying that currently we already meet load balancing. We're in the range of load balancing. The bottom end of load balancing, if we're assuming total dead load, 50% load balancing, we would need a force of 336 if we use a CG of 2. So the drape is essentially static. And the high end of load balancing, let's say force required is 673, that would give us 100% load balancing. But to meet the stress, our stress is slightly over. We can see that. That's our current stress. We're over by about 3.5%. If we increase the force to 433, then we would meet the stress. Now we could just look at this number and say, okay, I'm going to add one tendon, because I know that if I just add a tendon, we're going to get that force increment. Or we could go here to apply to model, and it's going to actually model that change. It would actually either distribute it over the current tendon, so we would just add 0.24 strands. You could distribute it over one tendon out of a group. In this case, it doesn't matter because we only have one tendon. Or we could add a new tendon. We're going to add a new tendon, and before I actually do that, I'm going to go back here to settings. I'm going to say use whole number of strands. Okay, and I'll come back to Optimizer. And here's our estimate. So now this jumps up a little because we're using whole number. I'm going to apply that now to the model. We need 2 additional strands in this span, or we're going to just add a new tendon. And I'm going to add a new tendon. The new tendon is, we're going to create one tendon. It's going to be a partial tendon from section C. So section cut C, remember, that cut is actually over here. So what's going to happen is the program is going to create a tail, and it's going to actually add another tendon out. Again, the user could do this manually. You don't need to rely on the program adding it for you. But we'll just go ahead and use this option to use the add tendon, and we'll say apply. And there's our add tendon. I'll go ahead and exit. There's the add tendon that was created. There's 2 strands. This is the shape of the add tendon. You could manipulate it. Now it's kind of decoupled from that optimizer. It's now just a component in the model. And we could rerun the analysis. So with that add tendon, I'm going to analyze this again. And then I'll design my cuts again. Oops, I don't need to generate them, I just need to design them. If we go back and look at the bottom stress, we'll go to bottom here. You can see we're a little bit low. So once we plug the tendons back into this model, what might happen is that this is a finite element model, so some of that load could shed. You know, depending on where it's anchored, we might get load shed away from the actual location that the program's integrating over, and you could get some variance between the optimizer and the actual finite element model. Sometimes it takes a couple of iterations to kind of target and get down to where we need, but this is close enough. We'll say that that satisfies the design requirement. So that's just an example use of the optimizer. The optimizer does not need to be used. The user could just add tendons to a model. For example, if I wanted to add tendons to this model, let me go back to my default display. I'll turn my tendons on. Let's say I wanted to add that tendon here in this middle span, and also let's do an add tendon out here. So I'll add a tendon here first. We'll just say this is the start of the tail, let's say. I'm going to go perpendicular to this slab edge. This needs to be inside the beam so we can reference the beam for the CG. And then we'll go out here and press enter to enter that cable. So this cable is just a default kind of a user, not a default, but a customized cable by the user. We'll add 5 strands. We have our stressing setting, and then we can manipulate, let's say this tail, we'll say it's a cantilever down, and we're going to drop that down, let's say 3 inches, and drop that up 3 inches, or raise that up 3 inches. Then over here we're saying that's 9 inches. So there's one add tendon. We have add tendon on this left side, right side, and then we're going to do one right in the middle. So on the middle one, I kind of separate these on the beam so I can actually see them in plan view. We're going to just start our tendon here, let's say, and we're going to stop that thing over here. So I'll turn back off snap near so I can snap perpendicular, and now I have this add tendon here. Now if I go to a, let me show this view here. So this tendon is the one we're kind of looking at. We'll say it's 5 strands, but I want to raise this up into the beam, and so right now this is dropped quite a bit low. If I say this is 0, just to kind of see where it's at, you can see it's actually being referenced from the top of this slab on the left side and the right side, and it's a 16-inch raise. So we're going to drop it. We're going to say that this is actually negative 13 inches. It's almost like the offset for the beam. Negative 13. Actually, let's use negative 10. That's too high. And then here we'll say this is negative 10, and this will be 3. And then you can see there's now that tendon in that beam as well. Okay, one way to confirm some of the geometry is to use the, we're going to use the rendering. So we'll go to the rendering. I'm going to go to a wireframe, and we could turn off the columns. That might be easier to see. And then we can see those tendons in the members. Okay, so this is a nice visual tool that allows you to verify the placement of those tendons. We'll say that this is the final design from a PT standpoint. Again, the user would have to interactively kind of use these tools here to view results graphically while you're going through the design. And we'll say that these tendons are what we want for these beam designs. So the next thing we're going to do is let's just reset and run the analysis again with these new tendons added. After we finish the analysis, I'll come back to floor design and design the sections again. Okay, we've included the strength check also in the design. So again, we're assuming that the PT design is done. That might actually take a few more iterations when you're working with this in the program. But we now want to produce some results, maybe deflection results. That might be part of the iterative process, as well as reinforcement results. Let's look at deflection first. If we go to the, let me turn on the default display here so I remove the tendons out of view. If I go back here to analysis, design sections, deformation, you can see on the strips we can see the deformation for the beams. Now this does not include long-term effects. This only is whatever load combination is set here. So this is service total without without recognition of long-term effects. If we want to check cracking in long-term, then we would need to add those combinations into this box. I could add long-term combo. I can define a creep and shrinkage factor. The program will add a sustained crack deflection combination. The user can modify this. This is just an easy way to get a couple of very simple combinations in to produce this check. The user can customize multiple crack deflection combinations and long-term combinations as they see fit. The long-term combination designation is really, this is technically called the analysis and design option type. This just allows the user to set or to combine the results of other combinations. So here we're saying the creep factor was 2. We're going to take the instantaneous sustained plus the creep factor of 2 times the same combo, and that gives us 3 times this result here. So if I do that, if I add that combination, I need to actually reanalyze again. So we'll go here to execute the analysis again. We've added 2 combinations. We have to update the results. Okay, I'll redesign the sections again. When I redefine or redesign those sections, now I have results under loading. You can see I have cracked long-term deflection results. So if I go to the long-term crack deflection, and I'm actually going to turn on the beam deflections here, because if I go to deformation, you'll notice that actually doesn't show up for long-term combos. For cracked, technically it's for the cracked combo. If I check it for long-term, it will show up, but this does not include cracking. So the program integrates over the shells for the basic load cases and combination solution. The crack solution is a post-process that is not really stored in the data that's being used to actually integrate to produce this result. So the long-term uncracked deflection here is 0.6 downward, 0.2 upward, 0.3 downward. If I go to cracked, you say, well, that's not there. But there are other ways to show that. So if we go over here to analysis, and I go to beam deformation, and we're going to look at the beam deformation in the Z direction. Let me turn off this. Actually, we want to go, instead of beam, we're going to go here to slab. This is the one we want. So slab, Z direction displacements for the long-term deflection. Make sure we have the right load combination selected here. Okay, so this is the deflection for long-term with uncracked condition. If I select cracked here, you'll notice nothing shows up. This would mean that the loss of stiffness is essentially negligible. I effective equals I gross, so the contours are actually identical in this particular case. If you look at the sustained deflection, this is 0.3 inches versus this is the uncracked condition versus the cracked condition. You can see this is also 0.3. And further to that, if we actually go over here to analysis using the cracked combination, this is cracked underscore sustained, you can see that for beams, if we check actions, we can actually look at the reduced stiffness ratio for the elements. And that can be done for the beam or also for the slab. So if we look at the reduction here, this will essentially yield no result because there's no reduction in stiffness for this particular case. And that would also bear itself out potentially in the stresses. So in our case, if I come back to the sustained level combination, just the regular service combo, and I look at the stresses along this strip. Let me go back here to stress. I'll just collapse that. And under design section stresses, we're going to look at the bottom stress. You can see this is essentially all pre-compressed here. This is in compression. This here is around 210 psi. So if we take a 5,000 square root and we divide 210 by that, that's about 3 square root of f prime c. So nothing is cracked. We have enough PT in here where the beams are almost fully pre-compressed. That's why we're not really seeing any crack deflection results for this member. But you can still check it by setting up the combinations as was done there. So the next thing we'll look at are the, let's go ahead here and look at the reinforcement. I'll come back to my default display. Graphically, I can go to Rebar and I can just calculate the rebar plan for the envelope or for any other of these selections, individual combinations, or envelope of surface and strength. We'll just use the envelope. And the program will show us what reinforcement is required for this beam. This is in plan view. If you want to see something a little bit different, we can go back to the strip. I'll double click on that strip and then I can generate a elevation of this. So we'll come up here and just generate an elevation, and this will show us shear stirrups bars in this elevation view. So this is another way to obtain that information. Anything that you see graphically that you want to include in a report, it's important to take a snapshot of that. So we can go to reports, say this is information I want in my report. I'll just take a screenshot. I'll just say beam elevation. Okay, maybe I also want to check and look at the stresses under total condition or sustained condition. So any state of graphical viewing that you want to take a screenshot of, we could do that. Here I'll say stress, sustain, bottom. And these types of reports or these graphical screenshots that we're taking are producible in this report compiler. So if we come here and I go down here to graphical screenshots, those get added into the report that I'm going to create. My recommendation is to produce a graphical report separate from a tabular report, so there's additional options here for tabular. We can go to File and I can generate that compiled report here for these two conditions, and this will produce, in this case, a PDF file of those images. Okay, this is the report that I just created. We have our elevation and our stress report. And again, there are additional reports that you could set up in a report from this compilation window. If we wanted to utilize tabular reports, we could go to Reports, Design Strip Data. Everything that we're kind of evaluating is on the basis of a design cut. So this is all entered here under Design Strip Data. We can produce design section forces, rebar capacities, and then this is more input, dimensions of the sections, geometry of the sections. So these are all tabular reports that would be produced. One thing I'll show in terms of the graphical reporting, again, we'll kind of come back over to here, is if the user wants to see capacity, we can go to Investigation. I can produce moment capacity. Blue is negative, green is positive capacity. And we could also show the demand, the envelope of demand with the capacity. That's the gray that we see there. The best way to produce this, again, is a vectorized PDF. I would take a screenshot from here and add it to the compiled report. We could also look at reinforcement along the strip. If I want to know what the envelope of reinforcement is, graphically, I'll produce that here. The calculated reinforcement is shown here. Green is negative, blue is positive. And this gives me a decimal output for the reinforcement. And we could also show the provided reinforcement. This is what the program actually provides versus the required. And that's based on these bars that you see. This here is 18 number 5s and so on. So the bars are kind of hidden underneath there. I could actually come back to floor design and just turn off the section cuts. That helps us see a little bit better. Okay, so there's additional reinforcement reporting graphically here. If you want to change the bar sizes that the program is using, we can go to reinforcement and define the size of material here for beams. Top and bottom, stirrup sizes. Material assignments are shown here, but that's actually defined under criteria for rebar material. Okay, so there's a lot of opportunity here for the user to just model simple beams, continuous beams, and use Builder in this format to generate designs and evaluate beam frame type systems. If you have any questions, please contact support@adaptsoft.com.